So, yeah, this was initially all focused on CAMs or convection-allowing models, but I've added some on models with convective parameterization. So, obviously a lot of credit given to Steve Weiss and Jack Kane, who put some of this material together, and I've kind of added to it over the years as I've given this lecture. So, none of this is new here on this slide. Basically, for severe weather forecasting, we have basically an incomplete knowledge of all the processes, obviously, in deep moist convection, but also the environment out there. We only have very seldom measurements spatially and temporally, so we don't really have a full knowledge of what is out there, and also, of course, all the processes involved. But obviously, some of the basics we certainly understand: moisture, lift, instability for thunderstorms to form, wind shear, help determine whether it might be severe, the convective mode associated with that, so the variety of storm modes that are possible. And then, of course, the timing, convective initiation, where they might occur and when, and then how they're going to evolve over time, obviously. That's important as well, because you get a variety of evolutions based on different environmental parameters, wind shear, forcing, and so forth. So clearly, observational data is important in assessing the current state of the atmosphere, but if we want an outlook for tomorrow or days after, we have to use numerical weather prediction models. And so it's heavily used, obviously, in severe weather forecasting for, things a few hours to several days in advance. So again, none of this will be new, but if you really think about numerical model, different aspects, we obviously have a set of governing equations, physics of the atmosphere that we have to integrate forward in time. We obviously have a specified domain for our model. We have a set of methods that we use to solve these equations. A lot of approximations involved with that. We have a set of parameterizations, of course. There's a lot of things that we can't resolve in the atmosphere. Obviously, small-scale flow features and so forth that we can't resolve, so we have to use parameterizations. And so they're basically just ways to represent these processes in the atmosphere, since we can't resolve them directly. And then, of course, there's initial conditions and boundary conditions, where obviously initial conditions, we use observations from the atmosphere to give the best state of the atmosphere to integrate forward in time using the equations and parameterizations. And then boundary conditions we need, obviously, in a limited area model. If we don't have a global model, we need to feed boundary conditions with that throughout the integration period. So basically, numerical models is the result of all these choices, approximations, and compromises. I mean, if you really dig down into it, there's, a lot of uncertainty involved with, and a lot of approximations and estimations and so forth within it. So you can imagine that those errors can propagate significantly over time as you move forward. So we'll talk about some of those. This is kind of an interesting slide. This is something that Brad Ferrier at the Environmental Modeling Center produced, which is the modeling center for the Weather Service. Basically, they do all the work on operational models. And so he has this thing he calls the physics wheel of pain. And as you go to higher resolution, he equates that to being higher pain. So if you look at this, this is a involved diagram showing lots of the interactions between the different parameterization schemes within a model. And it's very complex. And if you tweak something for one thing, you may have unintended consequences on other aspects of these parameterizations. That happens all the time. Brad, for example, he's a microphysics expert, and so we'll evaluate some of their models that they run at EMC and say, these storms in a convection-allowing model, they don't really evolve into an MCS like we'd like to see. We'd like to see more stratiform precipitation. So they go in, and there's all these estimations, approximations that they use, and you can tweak those around and try to get better conversion to ice or whatever in the cloud, and then that can play into other things. You have unintended consequences, then maybe you impact the surface temperature or something, you get the result in the storms maybe look more realistic, and then you have some negative consequences as well. So there's a lot of interactions involved here. The first one listed there is hydrometeor phase, so liquid, ice, so forth. And then obviously the different phases will have different optical properties. What's the coverage of clouds? What's the overlap of clouds, the depth of clouds, and all that. So that's all within the microphysics, and then that can obviously feed back to the radiation, how much radiation is reaching the surface, how much is reflected back to space, and so forth. And we've seen a lot of those issues with recent RAP and HER. They've done a lot of physics work to improve cloud fraction, subgrid scale cloudiness because they had a really strong warm dry bias in the warm season. They've done a lot of physics improvement to increase subgrid scale cloudiness. Second one there, precipitation. That obviously impacted microphysics, how much precipitation reaches in the ground, so that'll affect the surface scheme and PBL scheme. Third one there, subgrid transports, stabilization, detrainment. That's between microphysics and cumulus scheme or convective parameterization. The fourth one there, surface energy fluxes. So between the radiation and surface PBL. And then the fifth one listed there is obviously how the surface layer warms, PBL deepens, mixes, and so forth. And then you get shallow convection, deep convection, and so forth. So it's a very complex and interwoven aspect of modeling that really is complicated. So another aspect of this is what your model resolution is. And so sort of this, you've probably heard of this physics no man's land there, sort of where you're starting to resolve some of the things very crudely, some processes very crudely, where at larger scale, say greater than 20 or 30 kilometers, a lot of those you obviously aren't resolving them, so you need parameterizations for them. And as you get to finer resolution, higher resolution, you're starting to resolve some of those better, so you no longer need a parameterization scheme, where you start to get feedback between those things. So there's this area roughly between 10 kilometers or so and 4 kilometers roughly, where you generally want to stay out of that, just because you're starting to resolve some of these processes, and so you don't want to sort of double count with a parameterization scheme and also start to resolve them. So that's why you see generally, the NAM has run at 12 kilometers for some time, the RAP at 13 kilometer grid spacing for some time. GFS now is approximately, it's a spectrum model, so equivalent around 13 kilometers or so effective grid spacing. And then our convection allowing models jump down to 4 kilometers or 3 kilometers or so. So we try to avoid that physics no man land area there. Okay, so this is somewhat I added at Ariel's request for this year, is just talking a little bit about some of the models with convective parameterization. I'm going to really focus on some of the issues with the model, so that's just kind of one thing I do in my job, is I have to evaluate. EMC will have their next version of a model, and I get a look at it and scrutinize it and compare it to the existing operational version and get to see some if it's really improved or not for aspects of SPC. But of course, with NWP, numerical weather prediction models, you really use them how you might, diagnose severe weather from observations. Especially at longer ranges, you'd look at pattern recognition, the evolution of a shortwave trough, for example, its orientation and propagation. So, that type of thing, that the surface pattern, frontal boundaries, and all those things, that's obviously how you would scrutinize model information. Obviously, the ingredient-based approach, moisture, instability, lift, vertical wind shear. So, you sort of can perfect prog a model and do it as you would diagnose observations of those types of things. But the obvious problem is that models aren't perfect, so you have to really understand the biases and limitations of the models. I mean, without that understanding, it's really difficult to get a good forecast, beyond the next few hours because, there's lots of issues with models. I mean, they've certainly improved a lot with time, but really understanding their biases can help improve the forecasting using models in that regard. So I'm just going to kind of step through some of the operational models and basically go through some cases of some of the issues that we see. So I'll start with the NAM here. Just go through a case here from August of 2015. It's not SPC's best day in terms of a convective outlook. You can see in a large enhanced area without any reports, basically, extending from central Minnesota down into southeastern Nebraska. And so I think what this will show, and you probably see it as well if you watch these often, the outlooks are obviously strongly influenced by model output, and if models have a certain bias and you sort of don't pay attention to that, that can come back to cause a forecast like that. So here's NAM 2-meter dew point forecast. This is, I believe, a 21-hour forecast, yeah. So the green is this is the difference between the NAM 21-hour forecast and the SPC mesoanalysis, which is a RAP-based analysis, essentially, that incorporates observations. And the lightest green is 5 degrees Fahrenheit, and then the next shade of green is 10 degrees Fahrenheit. So you can see from basically, let's see if I can get this mouse, basically from eastern Oklahoma all the way up into the Dakotas, you have pretty strong moist bias in the model run. And it's really obvious when you look at the SB Cape forecast at the same time. I think there's like 4 shades of red there that goes to 2,000 joules per kilogram too high, over forecasting instability. If you look at the NAM a lot, you see that a lot, right? So it's sort of worst case scenario oftentimes. And so if you dig down a little deeper, a lot of what we do at SPC, we obviously examine forecast soundings a lot in what we do. So here's the observed Omaha sounding. They had a special sounding 18Z for this day. It's probably hard to see some of the details here. It's hard to see it on this screen as well. And I'll advance forward to overlay the NAM forecast sounding 18Z valid at Omaha there. And you can see a very significant moist bias compared to the observed sounding, which is now in the back there in purple. And this oval area down here is the 100 millibar, lowest 100 millibar mean mixing ratio. Just gives you a pretty good idea of sort of the low level moisture looking over a depth, because you can see there's a lot of, this is the observed sounding, a lot of skin moisture basically. It's much drier just off the surface. And that's, I think it says 13.5 joules per kilogram. This is on the order of 15 grams per kilogram. So, obviously if you have way too much moisture in the forecast sounding, vertical profile, you're going to get a lot more CAPE and expect a lot more severe weather than might occur. Here's a Topeka sounding. This is valid at 0Z, so a 24-hour forecast we'll look at. This is the observed one. I think it's pretty dry, obviously, aloft at 850, roughly 15 grams per kilogram, and then the forecast sounding much too moist. So this may be somewhat of an extreme example, but it's not that uncommon to see, much too high moisture in the low levels in NAM soundings. It goes back to parameterization schemes, surface layer scheme, PBL scheme, and all that. So it's just one example. Here's another example. This is a more recent case from December 25th. This was first Christmas Day tornadoes in Kansas, since records were kept in 1950. This is one of the cases was looking at to compare the parallel, which is now, it became the operational NAM last month, and the operational NAM at the time on the left. The top panel shows surface isobars, sea level pressure, and shaded's a 2-meter dew point. on the right top is then the parallel version of the NAM. And you can see pattern-wise are very similar. The bottom panels show the MU CAPE, and then the green contours are 0 to 3 SRH. So you can't really see the blue vectors are 0 to 6 shear. But in general, it's pretty similar pattern. Again, when you dig down forecast sounding wise, you start to see some real funny things going on. So on the left, that's the operational NAM. Notice that it's saturated over quite a layer with very steep lapse rates. And so that's not generally that physically realistic. So, having saturated near dry adiabatic lapse rates, that can be a problem. And it doesn't really accentuate the CAPE that much. It is a little higher on the one on the left than the one on the right. The one on the right looks a little funny at the top of that, but they've made some adjustments again to the convective parameterization scheme that they weren't accounting for in the previous version. And then this next time, which is just an hour later, this is a 16-hour forecast. Notice the one on the left, it's super adiabatic, saturated layer in the forecast. So, and it's right above a very strong vertical motion area. The one on the right, it's, I think, a little more physically realistic, though it looks a little funny in itself. But again, these are things that, it's really not, it wasn't, in the previous NAM, it wasn't hard to find those moist adiabatic, absolutely unstable layer, or mols in the previous NAM. They've made some corrections to improve that. So again, some of the common biases that we see. GFS, highlight a couple cases for this as well. This is July 16th of 2016. We had an enhanced risk across northern South Dakota, southern North Dakota. Here's a mesoanalysis for 2-meter dew point for this day, typical summer day, highlighting the 56 Fahrenheit isodrosotherm there. And then here, there's the moist axis across Mississippi Valley up into eastern Kansas. Here's the GFS 21-hour forecast of 2-meter dew point, and then the white line is where that 56, or where the light blue was in the observations or best estimate from the mesoanalysis. And you can see the moisture in the GFS forecast is much farther east. And so this was, and still is, a common issue with the GFS. On the edge of moisture in the high plains, too much mixing in the PBL, so you get too deep boundary layers, too dry, and generally too warm. The moist axis, it doesn't look too bad. So it's kind of an interesting thing. It's where are you at with respect to the moisture. Tends to, on the edge of the moisture, especially over the plains, overmixes, but within the deep moist sector, it doesn't actually do too bad. So, it's kind of location dependent based on the moisture itself. Here again is a difference plot in the upper left. The GFS 21-hour forecast of dew point. That's the actual dew point forecast. The difference is on the right there compared to surface OA. And the browns, the darkest browns, which exist there across western Nebraska, southwestern South Dakota, eastern Wyoming. It's over 20 degree Fahrenheit too dry. So short range forecast, still, it's just way overmixed, way too dry. And you can see in the bottom left there that initiation of actually what became severe storms there into western South Dakota. And that's where the strongest dry bias was from the GFS. So, that's not very helpful to forecasters if you're trying to, create an outlook based on that. It's just, so it's, again, a bias that you have to, understand, that you learn from using it and looking at it every day. But it causes a challenge for interpretation. So look at a couple forecast soundings. First, here's the observed in Amarillo in the Texas Panhandle. I'm not going to be able to read the numbers off of that, but it's, it is pretty warm and dry there in the observations, but I've underlaid the observed in purple now with the forecast, 24-hour forecast from the GFS in the red and green, and you can see, way too deep of a boundary layer. It's a little warm. It's not terribly bad on the temperature, but the dew point's way too low. So that's the type of thing we see up at Rapid City, where we had severe weather move through. Now this is the observed sounding is convectively contaminated. So I don't underlay it on the next slide. But here's the forecast PBL. There, Rapid City was about 80/60 before convection came through. And this forecast sounding is 92/38. So it's just off a little bit. So, those are concerns that we have, and as a forecaster, you get to look at it. The interesting thing is that a couple versions ago of the GFS, it tended to be a little bit too moist. It tended to have kind of a moist bias, and they made some changes to their PBL scheme, and now all of a sudden, it overmixes the boundary layer too much, on the edge of a moisture gradient. So that's really hard for forecasters, that when biases change that strongly from one version of a model to the other. And that's why we do these evaluations when they're ready to put out, the next model version. If we can't give our forecasters heads up at all, they'll figure it out soon enough, but it's good to give them heads up before something comes out that is a significant change, like the GFS was several years ago. And they've tried to make improvements in the latest versions. They're slightly improving this dry bias, the overmixing bias, but still persists. Okay, so go forward, we see these types of issues. So, maybe an ensemble approach will help, and certainly that's a good idea. Obviously, there's model errors. We already saw some cases of that. You have imperfect initial conditions. Certainly, we don't have a great measurement of all aspects of the atmosphere, certainly. So an ensemble approach is one way to estimate the uncertainty of the forecast. But ensembles aren't perfect either. They're made up of imperfect models, which is one of the issues. But also we don't really know how to assemble an ensemble that well. So I'll show some of that. They're really under-dispersive, meaning they don't have good spread. You want to encompass, in theory, the observations within the model, the ensemble forecast. But I'll show here that a lot of times that's not the case. The solution, the atmosphere, often lies out. The observations lie outside of the ensemble forecast. So basically, all ensembles generally provide overconfident probabilities or overforecast probabilistically. So let's look at the global ensemble forecast system, which is basically an global ensemble made up of GFS. And I will say, one of the issues that we see operationally with the way this implementation is done is they upgrade the deterministic GFS. And so in theory, you've improved the deterministic, but the ensemble does not get upgraded at the same time. And so what you have is the current operational GEFS is actually, later this summer, it will be 2 versions behind the operational deterministic GFS. And so you carry some biases that are really negative for several years in the ensemble that have been removed in the deterministic run. And so that's a really bad aspect of the implementation. So we hope that will go away in the future, where we implement the deterministic and ensemble upgrades at the same time. Okay, let's look at case here for the GEFS. This is September of 2015. We had enhanced risk for hail over northern Kansas. Indeed, there was a lot of hail reports there. One of the neat things you can do with ensemble forecasts, and I really like to use them in this way, which is to do what we just call it combined. It's roughly a joint probability of several aspects. So convective precipitation, CAPE, and shear. And it really can, the higher probabilities, it's hard to get high probabilities when you're multiplying 3 probabilities together. even if you had 90% of all those, you know, that's still only roughly 70% or so when you multiply them together. So you can really get to see where the overlapped Cape shear convective precip is from this. And so that's one of the advantages, obviously, of using an ensemble is you can really combine a ton of information from several model runs into a nice compact display like this one. So this was the old GEFS. And so this was, again, a time when we were evaluating the next operational version, which is on the right, and it is the current operational. And something stands out here, and this was not expected at all, because a lot of times when you evaluate these parallel runs, there's not that much difference between them. I mean, there's generally small tweaks, and so the resultant forecast doesn't usually vary or differ from the previous one that much, but you can see high probabilities, or relatively high probabilities from the old version to much lower probabilities where we had, you know, all those hail reports there across northern Kansas. And so it's like, what's going on? That's unexpected. If you look at some of the components of that, the Cape probabilities, you can see an axis of higher instability extending up into the Kansas and Nebraska area there on the left. And it's largely absent in the parallel run on the right. And the dashed yellow line, this is the 1,000 joule per kilogram median line, there extends up into southern Nebraska. It only extends into northeast Oklahoma, another version. So clearly this is a day 3 forecast. There's something much different in that latest version of the GEFS. And so looked at some other things. This is the mixed layer LCL, probability less than 1,500 meters. So you have pretty high probabilities. You're kind of on the edge of the drier air there in the old version of the GEFS. But notice that basically there's none of the members have low LCLs across that area. In fact, you have this, you know, notch that goes all the way up into the Great Lakes where you have higher LCLs. And so clearly it's a mixing layer. It's too much mixing in the PBL scheme. So here we go back to the physics, the PBL's parameterization for this example again. And so guess what? This latest version of the Ensemble has a over-mixing, and now you've propagated that into 21 members. You have a bad deterministic forecast because of that issue, and now you've put the same thing into 21 members, and they all have the same bias. So now what should be an advantage using, excuse me, an ensemble, you've made an issue because of that systematic bias. So it's one of the negatives that we have to deal with, and unfortunately the GEFS will not be upgraded probably for almost 2 more years because they're waiting for the FV3, which you guys, I'm not sure if you've heard, it's the next generation global model. It's going to replace the GFS, and so they're going to implement that deterministically, and then they'll eventually be the next global ensemble will be FV3 based. Okay, let's look at the SHREF. So hopefully it gets better, right, at mesoscale. Well, the last version did actually get better. So this shows an example of that. So this is a spaghetti plot, basically lines of constant heights, 5640 meters, 500 millibar height. So this just shows all the members as lines. I'm sure you've seen these plots before. And this is a 0-hour forecast. So this was what we had to deal with for a couple years in the previous version of the SHREF. The lines, you can't see any difference between the lines because there really isn't any spread in the initial conditions of the ARW members. So what do you think happens in the forecast? Well, there's not much difference in the forecast. When they start the same, they're probably going to end pretty similarly. So this version on the right, again, we were comparing versions for what would be implemented. I think at the October or so of 2015 is when the one on the right became operational. And the ARW members now are in red, and you can see difference in the lines in the initial conditions. So little spread at the start, which is good. Here's another way to look at sort of member spread. This is from the SPC SHREF Plumes page. So the top is the forecast of 2-meter temperature at a given location. And you can't see, again, the separation between the lines. There is no spread, basically, in the 2-meter temperature forecast until you get to about forecast hour 33. So, again, it's starting too similar. Didn't have enough diversity initially, where the next version is a little better. There's a little more spread amongst the 2-meter temperature forecast. The red dots are the observations, and this is what I was talking about before. Notice how the observations, much of the forecast in the top one, fall outside of any members. So you have, 21 members on top, 26 members on the bottom, and a large portion of the forecasts are falling outside of the temperature forecast from any of the members. It's a little better capturing the observations in the bottom panel. Okay, here's what we call a rank histogram plot. So this is looking at 2-meter temperature of what's now the operational SREF, and there's 2 model cores within that. One way to get diversity in Ensemble is to use different model cores. We find that to be an effective way to do it. So WRF ARW core in purple and the NMMB cores in blue. And so in a rank histogram, what you'd like to see is you rank the observation relative to the member forecast at every grid point. And what you'd like to see is a flat distribution across, where the observations often fall somewhere amongst the member forecast. But when you start to see this U, this is sort of an extreme U shape. So in this example, the temperature is ranked highest. It's warmer than any of the members, so it means we have a cold bias in the Ensemble forecast. You can also see some observations fall on the cool side even. So that's not really a very good attribute of an Ensemble, to be U-shaped like that, and that's pretty extreme. This is a relative frequency, so about a third of the time the observations, 2-meter temperature observations, are warmer than any of the Ensemble member forecasts. 2-meter dew point. So again, ARW is in purple, NMMB in blue, and you can see which one has the moist bias. It's the purple one there, with over a third of the time that the observations are drier than the model forecast of the ARW members. Notice the blue is a little bit better. You don't have those really high peaks on the extremes, but it's still U-shaped in general. But the ARW especially, you can really pick out the moist bias in that distribution. Another way to look at Ensemble forecast verification is a root mean squared error. This is 2-meter temperature, the spread there, and then I have the bias down here. So ideally what you'd like to see, the spread in the Ensemble about equivalent to the root mean squared error. So your error in the forecast, if your spread isn't as big as your error, you're going to have a hard time capturing, encompassing the observations with your Ensemble forecast. And then the bias tells you, which sign. The root mean squared error obviously doesn't tell you what the sign of the error is. The bias indicates, you can see a cool bias in the afternoons. For a 2-meter dew point, again, you're just seeing not enough spread in the Ensemble in general. We went from this blue, which was moist bias, to something on overall that's more of a dry bias in the afternoon and moist in the morning, that type of thing. But that's sort of a side effect. I went back to the rank histogram for the dew point. You can kind of offset. Notice that the NMMB is a little bit more often dry, has more of a dry bias. The ARW kind of has a moist bias. And so sort of artificially you get something that works out sort of fortuitously. It's not really designed that way. They're all supposed to be equally likely.